Let's take a look at sample problem 10-9 on page 258. In this problem, we've got a disk, mass of capital M, which is given, 2.5 kilograms, mass of small m, 1.2 kilogram. The string is wrapped around the disk and it's hanging, and the radius of the disk, R, is 20 centimeters. So we're going to let go of this weight, and we're going to let it produce a torque on this disk, and it will spin. Find out what is the acceleration of mass m, what is the angular acceleration of the disk, and what is T, the tension in the string. So how do we go about solving this? Well, we see that we have three unknowns, so let's try to come up with three equations that use the unknowns and the knowns that we have here, and then we can solve three equations with three unknowns. So let's first try and come up with an equation for the acceleration of the falling mass. So I'm going to use Newton's second law. The sum of the forces is equal to mass times acceleration. And there's two forces acting on little m. There's the tension in the string upward, which I'll call the positive direction, and the weight, which is downward in the negative direction. And I'm going to solve that for A. So there is an expression for acceleration. Now let's come up with an equation for alpha. We know that tangential acceleration is equal to r alpha, and we have to recognize that the acceleration of this block A is the same as the tangential acceleration at the edge of the disk, providing there's no slippage between the string and the disk, which the problem says there is not. So this A of the falling block is the same A as tangential acceleration of the disk. So I can solve that for alpha, A over R. And lastly, let's get an expression for the tension. I'm going to start off with my equation for torque is equal to I alpha. I is not one of my variables. Torque is not one of my variables. So I want to change those to include only the variables that I'm working with. I know that torque is equal to F times R perpendicular, and I recognize that tension is the force that's going to accelerate this disk. So I'll replace F with T, and I notice that they're already at right angles, so I don't need to worry about R perpendicular, it's just R. And the moment of inertia of a disk spinning about its center like this is 1/2 mr squared times alpha. So there we go. Now I've got all variables that I'm working with, and I'm going to solve that for T. This R is going to cross off with that R, and I get 1/2 mr alpha. And I see down here, if I want to, this would probably be okay, but I think what I'll do is I'll replace R alpha with A. So this is going to be T then is equal to 1/2 mA. And I notice that this is a clockwise rotation, so that is negative. So this torque is negative sign here, but I'm going to put it over here. So there's my expression for torque. In terms of M and A, my expression for A in terms of T, M, and G, and alpha in terms of A and R, all variables that I've got over here. Three equations, three unknowns. Let's solve it now. So here are my three equations with three unknowns. The first thing I'm going to do, where I see this T, I'm going to replace it with this expression here. And I see I have an A on both sides of the equation, so I need to simplify this and solve it for A. You can go ahead and try this. When I solve this equation for A, this is what I get. And then I can plug in my numbers And that gives me an answer of A equals negative 4.8 meters per second squared. Now that I know what A is, I can go up here and I see that T then is equal to 6 newtons. And then I just go down here and solve for alpha. Negative 4.8 divided by 0.2 equals negative 24 radians per second squared. We did it.